My name is Brian Nathan. I'm a graduate student here at the University of Texas at Dallas. I'm just starting my second year working with Dr. Laurie. I'd like to talk to you about keeping a methane emission inventory during the natural gas boom. Okay, we got the point. All right, so this is a brief outline of what I'm going to be going over. I'd like to start with the Earth's radiation balance in its atmosphere. Now, we consider the Earth to be a closed system. What I mean by that is that all the radiation that comes into it from the sun has to be absorbed and re-radiated and accounted for in a different way. This is a schematic taken from a paper in 1997, so the numbers are probably a little bit off, but it shows how those processes work. All the radiation coming in from the sun is either going to be absorbed or reflected by the surface, absorbed or reflected by clouds. The radiation that is absorbed by the surface has to be re-radiated in the form of long-wave radiation, which we recognize as heat. Some of that, again, will get absorbed by clouds and other gases in the atmosphere. And overall, the entire system is just considered to be trying to maintain this balance. And anything that upsets this balance is a process known as radiative forcing, where we consider positive forcing to be anything that tends the climate to increase in temperature, and negative forcing process to be anything that tends to decrease in temperature. Now, if we didn't have an atmosphere, the average surface temperature on Earth would only be about negative 19 degrees Celsius on average. Just to give you an idea of how important it is, at least for us to stay warm, that we have this atmosphere. So then that begs the question of, well, what is the atmosphere composed of? As many of us have learned from that in high school, it's about 3/4 nitrogen and 1/4 oxygen, which is actually a little bit closer to 78% nitrogen and 21% oxygen, where that extra 1% is made up entirely of trace gases. And I should also note that this is the composition of the dry atmosphere. Water vapor can account for up to 4% of the composition of the atmosphere over the ocean. But in general, this is what we're talking about, and the trace gases then contain specific types of gases that fall into the category of greenhouse gases. Now, a greenhouse gas is any type of gas composed of molecules that have the ability to absorb and re-emit radiation in the thermal infrared range. These are the four most abundant greenhouse gases in the Earth's atmosphere. We have water vapor, we have carbon dioxide, methane, and to a lesser extent, nitrous oxide. Now, of these, the most important greenhouse gas as far as keeping the Earth warm and those processes is far and away water vapor. We've known this since 1861 was the first time anyone mathematically was able to prove this. But generally, when we're talking about greenhouse gases, we don't consider water because water has the unique ability to change rapidly in response to changes in temperature and pressure of the atmosphere around it. It has the ability to condense, evaporate, and precipitate out of the atmosphere. Because of that, we consider water vapor to be a feedback process instead of a forcing process. Again, going back to that term of radiative forcing. So when we talk about greenhouse gases, we really want to focus on what we consider the non-condensing greenhouse gases. The most abundant one of these is carbon dioxide. And anyone who's been reading the news or not living under a rock for the past few decades knows that carbon dioxide is gaining concentration, especially as we burn fossil fuels. It's still a hot topic. And anthropogenic sources have contributed massive amounts of carbon dioxide into the atmosphere, which are now measured on the order of gigatons per year. This brings us to methane. Methane is the second most abundant greenhouse gas in concentration in the Earth's atmosphere. However, per molecule, it is over 25 times more effective at radiating heat. And what this means is we're going to be especially concerned about it, and we want to keep an inventory of what sources are creating the methane and releasing it. The methane, when we're talking about which sources it comes from, we like to divide it into two categories, natural and the anthropogenic. The natural sources, actually you can see a variety of sources are kind of matched up here. Among these, the natural sources would include wildfires, wetlands, and termites. Wetlands being the major source, actually contributing anywhere between 37 and 40% of the total amount of methane that's emitted into the atmosphere. But in total, the anthropogenic sources, which include landfills and energy drilling, including shale gas drilling, and actually ruminants coming off of cows, all total now contribute 60% of the total budget of methane. That's as of estimates in 2007 by the IPCC, which is the International Panel on Climate Control. Since the beginning of the industrial era, which we consider to be about 1750, we see that the concentration of methane has already tripled. So then the question is, well, how do we know this? What are our measurement methods? Before about 1950, we didn't actually have people running around taking air samples out in the field and calculating and tabulating the different concentration values. So in order to get an idea of what was going on back then, we had to rely on these underscore samples that are taken out of areas like Antarctica. And they actually serve as a variable timeline, but the air bubbles trapped in them being like a little time capsule of exactly what the atmosphere was made up of back then. Now, since then, there have been advancements in human technology. We have the ability to take a top-down view from instruments like satellites and airplanes flying overhead. We also have the ability to take air samples from these flux towers, which are set up across the globe, and they can take flask samples at different altitudes to allow them to actually get a flux reading. This is a map showing how they're kind of spread out around the globe. You see there's a cluster over in Europe, but for the most part, they're really broadly spread out. And then the problem is, when we're trying to get a lower resolution image of these, the lowest that you're able to find is about 1 degree latitude by 1 degree longitude, which converts to about 58 kilometers by 69 kilometers, or something about 4,000 square miles. Now, if you think about that in terms of the sources that we looked at, those things are not going to be 4,000 square miles. So if we want to actually figure out, how much is coming off of a certain wetland, we don't have the technology to look at these emissions on the regional scale. Now, going back to shale gas, which I mentioned is one of the emissions coming out of the energy spectrum, energy sector, not energy spectrum. This is a graph showing that there are a lot of shale deposits all over the United States, and these just contain massive amounts of natural gas, the primary component of which is methane. Now, in order to get at these, it's important for us to understand how much is down there. These are the estimates just as they're being updated. You see the legend, just the updates from 2006 to 2008, and how many trillion cubic feet of methane is trapped in these has already nearly tripled, or actually more than tripled. In 2006, 2 drilling techniques were combined that led to a bit of a boom in this industry. And that is hydraulic fracturing, which is colloquially known as hydrofracking, and horizontal drilling. Now, when these methods became combined, it allowed access to parts of these shale deposits that weren't previously accessible. So when the drill goes down, in fact, this is a schematic of what one of the well drilling sites looks like, taken out of Scientific American. When the well is drilled straight down, previously all they could do was send down the water, the sand, the chemicals in the hydrofracking process, crack the shale, release it, and get what they could. And they couldn't access any of this stuff over here. But now when they combine it with horizontal drilling, they can go an additional 5,000 feet horizontally and then crack all of the shale around it, then accessing much greater quantities. In fact, from 2006 to 2010 alone, every year, there was an increase in 48% production of methane coming out of just these shale drilling sites alone. Now, the unfortunate thing is we don't know how much is being released into the atmosphere at these sites. There's very little known about them because, again, we can't take measurements on a regional scale. We can only look at kind of the big global picture. Estimates from the EPA, and actually there was an estimate done, this was from Cornell back in August, just a few months ago, that fugitive emissions coming off of these well drilling sites put it at between 3.6 and almost 8% of the total amount of methane produced over the entire lifetime of the well gets released just during the drilling process. This is a graph. Every year, the Energy Information Administration puts out an energy outlook, and so this is showing the different types of natural gas and how they combine, how they make up their different components. You see, shale gas is not the primary component when we're talking about sources of natural gas. However, you can see distinctly the spike in 2006 when those two techniques got combined, the hydrofrac and the horizontal drilling, and the 48% increase every year, which led them, when they projected forward to 2035, to assess that by then, natural gas extracted from shale is going to account for almost half of the total U.S. production of natural gas. So, if this is the problem, what are we going to do about it? What is our vision? Well, our vision is we're going to be able to use these robotic helicopters to then take readings and gather flux measurements at a much finer scale. Instead of these square kilometers that we were talking about, now we can get a sub-meter scale, because if you think about it, all you need for a flux reading is a measurement taken at a different position or a different altitude. And we can, in theory, put these at any position and altitude within a reasonable scale without upsetting the FAA that we want. And as fortune would have it, the team here at UT Dallas Mintz has been developing these specifically for that purpose. This is the table that Alan showed, just listing the different types of measurements we're going to be getting using the helicopters. The top three are the ones that are important to me. We're going to be using the laser scanners, which are courtesy of, I believe, the geophysics department, to help us get a LiDAR topography of the map the area where we're going to be, or around which we're going to be taking these readings. We're also going to be using a trace gas laser sensor, courtesy of Dr. Mark Zonlo, who unfortunately couldn't be here, but him and his team at Princeton did a good job developing that trace gas laser sensor specifically for our helicopter. And we're also going to be using an FLIR 17-micron infrared thermal camera. So with the LiDAR topography, the advantage of that is we're then able to recreate in a software program called Console exactly what the terrain was over which we took the measurements. The benefit of the particle sensors, and there's handsome doctors on the benefit of the particle sensors is that not only are they using state-of-the-art technology, which combines not just the vertical cavity surface emission lasers, which is new technology also, but it combines it with quantum cascade lasers for the smaller particles like the nitrous oxide and carbon monoxide that would allow us to see if there are thermal processes that are probably leading to things. It gives us a much greater insight into where these things are coming from. And again, to our knowledge, these are the very first time any laser-based trace gas sensor has been developed specifically to be used on a robotic aircraft. The advantage of using the infrared camera is methane isn't visible in what we know as the visible spectrum. However, it does show up in the thermal camera because it is a greenhouse gas. So when we're using the thermal camera, we can then get greater insight into the areas where, hey, you know what? That thing, this pipe over here, it's releasing gas like a chimney. I think we should probably figure out how much is coming off of it, and then we can just fly over and take the readings and get a better idea of exactly how much is being released over there. Now, the most obvious question that we figured would pop up is, okay, well, if you're going to be taking basically in situ measurements on a helicopter, how are you going to get them with this giant rotor spinning overhead, blowing all the air out of the way? Well, although that's true for a helicopter that's even just hovering, these simulations are showing this at A is a helicopter moving at 10 meters per second, B is a helicopter moving at 20 meters per second, showing the air and how it's disturbed. The weight caused by the rotor is actually sufficiently behind it, so you see that the green portion of the air, which is actually undisturbed air, is almost completely where our sensor is going to be. So what that means is the weight caused by the rotor is going to be sufficiently behind it that we don't have to worry about it, especially because we're going to be flying these we're aiming to fly them at an average speed of 15 meters per second, which is right between the two graphs. So this is a simulation. Again, keep in mind we're still very early in the process, but this is a simulation of, I figured I could take a look at that picture of the chimney emitting methane and say, okay, well, if there was a mild wind, how would it flow? This was taken using the COMSOL software. We were able to recreate a very crude geometry of a chimney releasing methane, and it incorporates all the relevant equations of fluid dynamics and thermodynamics that we need to make this completely accurate. So in conclusion, methane is a very potent greenhouse gas. Again, it's more than 25 times more effective per molecule at absorbing and re-emitting heat than carbon dioxide. To date, there's very little known about how much is emitted at or around shale processing facilities and these well drilling sites. If we're going to get a better idea of what's going on here, we need to be able to take measurements at a much finer scale than the technology we have currently allows. And using robotic helicopters, we then have a way to do it. These measurements are then going to be taken, combined with the LiDAR measurements and used with the infrared that help us determine where to take measurements. And they can be put into COMSOL not just to simulate backwards in time to help us find possible sources of leaks around sites, but also then to simulate forward in time to show where the gas is probably going to disperse, which is especially useful around areas where cities and people live and are trying to breathe and might have respiratory issues. So I guess that's it. Thank you.